10. See electrical current and Ohm's law. 10th point 11. Introduction. Electrical discharges are short-lived because an object has only a limited number of excess electrons to lose. To use electricity to perform useful work, we need a continuous flow of charge. Electricity that involves continuously moving charges is called electrical current. Modern civilization could not exist without current electricity. Lighting, heating, and air conditioning, computers, televisions and radios, cars, and hundreds of other necessities and conveniences require electricity to operate. In all these devices, current electricity provides energy. 10th point 12. Electrical current. Current models. Nearly all electrical current running through solids involves the flow of electrons. Electrical current flows most easily through conductors, such as metal wires. The most common type of electrical wire is made of copper, although some wires are made of aluminum or copper-coated aluminum. Electrons may also flow through ionized gases, plasmas, such as those in fluorescent lamps, or even through a vacuum. Older televisions and computer monitors contain a large vacuum tube screen called a cathode ray tube, CRT, to display images painted by electrons. Physicists use several models to describe electron flow through wires. One is the electron diffusion theory. In this model, electrons move from areas of high concentrations to areas of low concentrations, just as gaseous perfume particles do when released into a room. Current is maintained in the conductor by a continuous supply of electrons at the source, which maintains this imbalance in electron concentrations. Another model that is perhaps easier to understand is similar to a stream flowing down a hill. Water at the top of the hill has a higher gravitational potential energy than at the bottom, so gravity naturally pulls the water downhill. As it flows, it can convert its potential energy into work, by turning a water wheel, for example. Similarly, electrons flow from a point of higher electrical potential energy in a conductor to a point of lower potential. A point that has a higher electrical potential is a source of charges. A point of low electrical potential is a sink for charges, a place how that charges flow toward. Conventional current flow. Electrical current running through wires and similar conductors is caused by the flow of electrons. However, that is not the way current was originally described. According to the model of electrical charges developed by Benjamin Franklin around 1750, electrical charge was a fluid. If a substance had a lack of fluid, it was negatively charged, and if it had an excess, then it was positively charged. In his model, current flowed from areas of positive charge to areas of negative charge. When, more than a century later, electrons were discovered to carry current, it was far too late to rewrite the science textbooks and equations. Most scientists and engineers continue to describe conventional current as the flow of positive charges through a conductor, which is opposite to the flow of electrons. This definition is actually not a problem, although it may initially seem confusing. Electrical current can also involve the flow of ions, charged atoms, in chemical current-carrying solutions and in some plasmas. In these currents, oppositely charged particles flow in opposite directions at the same time. Thus, defining conventional current as the flow of positive charges is satisfactory in all cases. You must keep this definition of current in mind as we continue our discussion of electricity. Direct current. Current that flows in one direction through a conductor is called direct current DC. You are familiar with many DC applications. Your cell phone, digital camera, and laptop computer are all powered by direct current, which is also the primary form of electrical energy for cars and most recreational boats and planes. Direct current power sources allow many electrical devices to be portable. The remainder of this chapter discusses only direct current. The other important form of electrical current is alternating current, AC, which we discuss in Chapter 11. For current to flow, there must be a complete path from B source of electrons through a conductor and back to an electron sink, which may be the same place as the source. This path is called an electrical circuit. To make an electrical circuit useful, it contains an electrical load, such as a light bulb, see Figure 10-23, which converts electricity to some other form of energy. If a gap occurs in the circuit, the flow of electrons stops because they cannot flow across the gap. Switch allows you to open or close the circuit by opening or closing a gap in the current path. 10.13 Sources of direct current. Since electrons are tiny bits of matter, the law of the conservation of matter applies to them. They cannot be created or destroyed. A steady flow of electrical current requires a continuous supply of electrons, so they must come from somewhere. Electrons can be supplied by two methods. They can be chemically released from atoms to do work one time, or they can be reused over and over again. Electrochemical cells and batteries. Electricity from a battery is a current of electrons used one time. A battery contains one or more electrochemical cells that supply electrons released by a chemical reaction to a circuit. For example, a standard flashlight battery is a single electrochemical cell. It consists of a zinc cylinder filled with a moist chemical paste. The bottom of the cylinder forms the negative end, or pole, of the cell. In the center of the cell is a carbon rod connected to the positive plus pole. A chemical reaction occurs between the paste and the zinc. This reaction releases electrons that flow through the metal can and become available at the negative pole. When you connect a battery to a complete circuit, electrons flow from the negative end through the conductor to the positive carbon rod. The rod carries the electrons into the chemical paste. A different chemical reaction at the surface of the carbon rod takes up the excess electrons to complete the reaction. Batteries that use solid or paste-like chemicals are dry cells. These cells are useful because they are portable, do not spill chemicals, and can operate in any position. Modern batteries used in most digital devices like cell phones and tablet computers use a different kind of chemical reaction. These batteries are rechargeable. Called lithium-ion batteries, they work on a reversible chemical reaction involving the movement of positive lithium ions within a paste contained inside the battery. As the battery discharges, the ions move toward the negative graphite pole. When charging, the ions move back into the lithium metal oxide paste. Lithium-ion batteries last a lot longer than standard batteries and can deliver more current. As long as the circuit is complete and the battery chemicals have not been used up in the battery, current will flow. When chemical reactions can no longer supply or absorb electrons, the battery is exhausted or dead. Ideally, a battery shouldn't go dead unless used in an electrical device. But in reality, unused standard dry cells last only about 1.5 years before they go dead. It's almost impossible to isolate the two chemical reactions for a long time inside the cell. Other batteries use a combination of metals and acidic liquid solutions or gels to produce electricity. These are wet cells or gel cell batteries. Most wet cells must remain upright during use in order to avoid spilling the chemicals. The main advantage of wet cells is that they can produce higher currents. The most familiar wet cells are the lead-acid batteries found in cars, trucks, and boats. A standard car battery consists of 6 wet cells connected together. Gel cells combine the liquid acid with other chemicals to produce a gelatin-like substance. These batteries don't have to be kept upright, so they're useful in motorcycles and in sailplanes, which operate at steep angles or even upside down. Like lithium-ion batteries, most wet and gel cells can be recharged using an outside electrical source, which reverses the chemical reactions inside the cell. Electrical generators. Sulfuric batteries are limited sources of electricity. Even in rechargeable batteries, the chemical reactions that produce electrons eventually stop because the chemicals are exhausted. Standard batteries then have to be replaced. Rechargeable batteries must be charged from another electrical source. A more reliable source of continuous electrical current is the electrical generator. Generators are machines that use the special relationship between electrical and magnetic energy, mentioned in Chapter 6, to move electrons through conductors. A generator basically consists of one or more coils of wire rotated in a magnetic field by some form of prime mover, such as a motor or a turbine powered by steam, water, or wind. You will learn more about how a generator works in Chapter 11. As a generator produces current, you can think of it as lifting charges to a higher electrical potential, like a pump that refills a water tower. The charges then flow through the circuit, losing potential energy. Eventually, they return to the generator at its low potential connection, which is like the low pressure inlet of a pump. The advantage of a generator is that the charges can be continuously used over and over again. Photovoltaic cells. Electrons are strongly affected by electromagnetic energy. When a light ray is absorbed in some kinds of semiconductors, an electron gains enough kinetic energy to jump from its atom and do work. Engineers have developed devices called photovoltaic, PV, or solar cells, that use this principle to power electrical devices located far from any standard electrical power source. When connected to a circuit, PV cells can produce a continuous current as long as they are illuminated by the sun or other strong light source. The energetic free electrons flow through the circuit and then reoccupy the gaps left in the semiconductor when they return. As with a generator, the electrons are reused repeatedly. 10.14 Voltage, current, and resistance. Potential difference. The volt. According to the conventional current model, the positive pole of a battery or generator is its point of highest electrical potential. Conventional current always flows from positive to a lower or negative electrical potential. The rate of current flow depends on the difference in electrical potential. Determining the electrical potential at a particular point in a circuit is almost as difficult as trying to determine how much thermal energy is in an object. It is much easier and more important to measure the difference in electrical potential between 2 points. The potential difference between any 2 points in a field or circuit is the amount of work needed to move a charge between them. We measure potential difference with a unit called the volt, V. A 1 volt potential difference requires 1 joule to move 1 coulomb of charge between the points. The volt is defined in the equation. 1 volt equals 1 joule over 1 coulomb. Batteries are rated by the potential difference between their positive and negative connections or poles. A standard D-cell battery is rated at 1.5 volts. A lantern flashlight battery is usually 6 volts. The battery that powers a smoke detector is 9 volts. A car battery is 12 volts. These potential differences or voltages determine the energy that the battery supplies to a circuit. Voltages are measured using a voltmeter. Electrical current, the ampere. The more charges that flow through a circuit in a given amount of time, the greater the electrical current. Electrical current is measured in the unit called the ampere, A, which is usually shortened to amp. Measuring electrical current N amperes is like measuring water flow by counting the number of liters of water that pass a point in a stream every second, liters per second. A current of 1 ampere is equal to 1 coulomb of charge, 6.24 times 10 to the power of 18 charges, moving past a point in the circuit every second, according to the equation. 1 ampere equals 1 coulomb over 1 second. Electrical current is measured by instruments called ammeters. Electrical resistance. How do moving charges do work in electrical devices? Consider water flowing down a stream, using some of its kinetic energy to rotate a water wheel. As the water exits the wheel, the water moves more slowly and has less kinetic and potential energy. Similarly, every component of a circuit hinders the flow of charges to some extent. This property is called electrical resistance. As current flows through a conductor, collisions between the flowing electrons and the conductor atoms add kinetic energy to the atoms and sap energy from the electrons. These collisions reduce the flow of electrons and cause them to accumulate at the higher electrical potential in the conductor. The more resistance a conductor has, the higher the electrical potential is at the end supplied by the current source. Consequently, the more resistive the conductor is, the lower the voltage available downstream. A special device called a resistor can change the voltage within portions of a circuit. In general, high electrical resistance is undesirable. Chapter 9 discusses how electrical resistance in power lines increases on hot days, raising the cost of electricity for consumers. However, in complicated electronic circuits, Resistance can be useful. Electronic components and complex circuits require different voltages. Using different kinds of resistors allows the voltage from the electrical supply to be subdivided into various voltages within the circuit. Because all electrical devices have some resistance, electrons always lose energy as they pass through a circuit. The law of energy conservation states that energy is never actually lost, but is converted into other forms of energy. This energy conversion can be used for beneficial purposes. For example, if you are making a coffee cake, you use an electric mixer to convert electrical energy into the mechanical energy necessary to spin the beaters. An electric oven converts electrical energy into the thermal energy that bakes the cake. Ohm's law. In 1827, Georg Ohm published his discovery of the relationship between voltage, current, and resistance in electrical circuits. He observed two things in a simple circuit containing a DC voltage source and a resistance connected to it by wires. As the size of the voltage source, V, was changed, and the resistance, R, remained constant, the current I measured was directly proportional to the voltage. In other words, if he doubled the voltage applied to a resistance, the current also doubled. As the resistance was varied and the voltage remained constant, the current was inversely proportional to the resistance. That is, if he doubled the value of the resistor, the current through the resistor was halved. Combining these two observations into a single equation yields Ohm's law. I equals 5 over R. This equation is commonly rearranged and written as V equals I times R. Resistance is measured in units called ohms. The symbol is the capital Greek letter omega. The ohm is defined from Ohm's law. It takes 1 volt of potential difference to draw 1 ampere of current through a resistor of 1 ohm. Rearranging the Ohm's law formula shows us that 1 ohm equals 1 volt per amp. R equals V over I. 1 ohm equals 1 volt over 1 ampere. Electrical resistance is measured using an ohmmeter. 10.15 Direct current and power. Power measures how fast work is done. See Chapter 7. It can be calculated by dividing the total amount of work done, in joules, by the time it took to do the work, in seconds, to yield the power in watts, W. In the same way, the faster a DC circuit uses energy or does work, the greater the power. For example, a 100-watt light bulb uses twice as much energy per second as a 50-watt light bulb. The extra energy produces more light from the 100-watt light bulb. Industrial machines that use thousands of watts of power have power ratings expressed in kilowatts, kW. We often refer to companies that sell electrical energy as power companies. However, the electric company usually charges you according to how much energy you use, not how fast you use it. The modern digital electric meter attached to your house displays the amount of electrical energy used since it was installed. Older models of electric meters use a spinning disc and a series of small dials with pointers. These dials serve the same purpose as the digital display, but also provide a visual indication of how fast the energy is used. The faster the disc spins, the greater the power usage. A 100-watt light bulb burning for 10 hours uses as much energy as a 1,000-watt blow dryer running for 1 hour. The light bulb uses 100 joules per second. The blow dryer uses 1,000 joules per second. The light bulb has to burn 10 times longer than the blow dryer to use an equal amount of energy. For this reason, electric companies compute the energy consumed by multiplying the power used by the amount of time it was used. Energy equals power times time interval. E equals P x delta T. Electrical energy is thus dispensed and billed in units of kilowatt hours, kWh. Electrical power in DC circuits is easily calculated from known quantities. Since a volt is related to work per charge, and since power is the rate of doing work, we can combine these concepts to develop the DC power formula. Power equals voltage times current, P equals V times I. Using Ohm's law to substitute for some of the variables in that equation, we can obtain other forms of the electrical power formula. As you can see, Watts, volts, amps, ohms, and coulombs are all interrelated. Studying these relationships is the key to understanding electricity.